Hello everyone, welcome to today's show on grade 12 differential calculus. Today we're joined by Twanette. Hello Twanette.
Hello.
And of course we have Dylan behind the computer working all the buttons. Now before we get into our conversations, remember that you can join the conversation by logging in, or not, well I suppose you log into Twitter and you follow the hashtag VTMaths. Join us in the conversation. Dylan will be watching the Twitter feed. So if you have any thoughts to add to this, please join us there. Now, Twanette, why don't you tell us a little bit about yourself?
Thank you for having me, Helen. I'm Twanette Knutse. I have been teaching maths for almost 15 years. I've been teaching in government schools in Cape Town and private schools. I'm currently teaching grade 10 to 12 at a private school close by.
Oh, fantastic. So you have a lot of experience within teaching mathematics. And how far have you taught in terms of grades? Where did you start? Some of us start in grade 4 and we move our way up.
I've only taught senior college.
Okay.
I have taught a year of grade 9 maths, but I've taught mostly 10, 11 and 12.
Okay, so lots of experience.
Yeah.
In that. And in all of the curriculums we've had in the last 15 years as well.
Yes, from the very old in Cape Town days to NSC to CAPS, and CAPS almost feels like I've went back to the olden days, if I can say that.
Oh, good. Well, why don't we start by looking at what's happening in grade 12? So the focus of today's lesson is on differential calculus. But before we get into that content, why don't you tell us where we've come from to get to differential calculus?
It's a long road, I suppose, but calculus is an isolated section in grade 12, but there's a lot that you need to know before you can actually do calculus. A lot of things you were taught in grade 10 and in grade 11. For example, factorization is an important thing. That was taught in grade 10 and in grade 11. Also, how to simplify and your graphs, your FX notation. Substitution, even the substitution method taught in grade 10 is very important. And it all helps you and it all builds up to calculus at the end of the day.
Okay, now in terms, you've mentioned pretty much everything except for trigonometry and geometry there. In terms of assessing where misconceptions could be, let's say with factorization, how would you do that?
I haven't mentioned trig or trigonometry that much. I don't think that that's really involved in calculus, but what I didn't mention was analytical geometry. The whole concept of differentiation is finding the gradient. And gradient goes back to analytical geometry a bit. A lot of teachers use the average gradient formula to introduce calculus. For me, it's assessment. I would, before we start differentiating, double check that they remember factorizing a quadratic equation, for example. That's quite important, even taking out a highest common factor. So a good idea would be to give a short assessment. 3 or 4 quadratic equations on the board to check that they remember how to factorize them. Taking out a common factor, like I said, you can also revise the gradient formula quickly so that they understand the gradient of a function can be found at any 2 given points.
Don't you find that so often taking out a common factor is overlooked or forgotten?
Oh yes, definitely. Definitely, but it's so important. In grade 10, I still teach that the steps for factorization is a common factor, even a common bracket. They overlook a common bracket and immediately want to do distributive law and start simplifying, which throws them off completely. But yes, definitely. But it's important. They can't differentiate in calculus unless they've simplified the function, especially if you've got a fraction.
I think you've touched on something very important there where you say they use distributive law, and then of course they've got this huge expression with it's a hodgepodge of everything. How would you show them, tell them to recognize that they have stepped wrong there?
I usually teach them they're always going to get an expression or a function. they have to, first of all, check if it's a fraction. If it's got a monomial at the bottom, remember a monomial is one term at the bottom, they have to split the fraction, put it over that monomial so that you can simplify it. Or if there's a binomial at the bottom, that's a clue. Maths will always give you a clue. If there's a binomial in the denominator, they'll definitely be able to factorize the top guy, either with a common factor or with a quadratic equation, and then your brackets will be the same. They must just use the clues that's given to them. There's always a clue.
You've touched on something really great there, the maths giving clues.
They always give you a clue. Well, I think so. The learners find it difficult to see them, but I've taught them. I often teach, look for the clues, and 99% if you've got a binomial at the bottom of the fraction, your quadratic will be factorizable with the same bracket. So they can also almost immediately rewrite that bracket and just try and figure out the second one.
Yes. Are there any other clues that you can think of off the top of your head about factorization that teachers could tell their students?
Factorization for me is, remember that they'll always tell you to factorize. If the instruction is simplify, then it's distributive law and foiling out brackets. Factorization, always the highest common factor first, then a common bracket, then the difference of squares, then a quadratic equation.
Okay, at the moment I feel like I've got a whole lot of words flowing past me. Do you mind just writing down a list quickly of what?
For factorization?
Yes. So these are the skills that they need to know before they start.
Before we start differentiating.
Now, what's nice about going through these very quickly is that those grade 10 teachers and even grade 9 teachers who are watching
always
can use this. So step 1 would look
highest common factor.
Highest common factor.
Always. Then you might have a common bracket. I call it a common bracket, which they'll also take out. It's more or less the same as the highest common factor, but your common bracket you'll take out and you'll be left with another bracket.
Okay.
The third one I call literally, for the kids, the difference of squares, and we draw them a square. Difference of squares will be a x squared minus a y squared.
Okay.
Our fourth step will be a trinomial, a normal quadratic trinomial, which we factorize, and that is almost it for grade 9. But when we move to grade 10 and 11, we can have a cubic equation.
And that's the difference in sum of cubes and
sum and difference of two cubes, which I also teach. Small bracket and a big bracket.
Okay, and the changing of the sign, where would that fit in?
Common bracket.
Okay.
Most of the time they'll do a switch around there.
Now, when I first started teaching maths, I wasn't the best maths teacher. I think I grew after a couple of years.
Yes.
And it was only 2 or 3 years into my teaching career that I started putting things out in step order like this. I found it solved a lot of problems.
For me, it's like a recipe. I really find, I suppose it depends on the teachers, but the pupils or the learners really benefit if they've got steps. If they see the word factorize, and I often see in my assessments that they write the steps down when they see the word factorize, and then they follow them, and then they can't miss out on a common factor. Because a lot of them will factorize a trinomial and lose marks because they haven't taken out the common factor first. Although perhaps the trinomial will be factorizable, sometimes not, and they must use the quadratic formula.
Yes, and that's of course quadratic formula is grade 11.
It's grade 11. And a grade 10 kid won't know if he hasn't taken out a highest common factor.
Okay, well, I think we've looked at factorization. You did mention some other things as well that they need to know before differential calculus?
Before differential calculus, factorization, very important. They have to know, I would say, the factor and the remainder theorem, where they are able to factorize a cubic equation.
Now, in the government schools, well, within the CAPS curriculum, not even within the government schools, they've done a section called polynomial functions just before this, in which they would have
definitely, as long as they are able to take a cubic equation, any cubic equation, x cubed plus 2x squared plus 3x plus 12, they must be able to factorize this cubic equation into a small bracket and eventually into a trinomial in this bracket, so that they can, in differential calculus, sketch a cubic graph which has 3 x-intercepts.
Unless, of course, it doesn't.
Unless it doesn't, unless you've got a double bracket, but mostly 3 x-intercepts. So what I just meant with that is they must be able to factorize using the factor theorem to get x-intercepts for your cubic graph. You can have a cubic graph with only 2 x-intercepts. Quite right, yes.
Of course, yes, like you said. Okay, so that is where it's coming from, and we've covered grade 9 and grade 10 content and some grade 11 with the quadratic formula. Where are we going to with, obviously it's grade 12, and we're just introducing differential calculus at this point. Is it going anywhere further than this within schooling?
No, I think calculus is quite isolated in grade 12. I think they must be able to find the first derivative. They do double derivative for point of inflection on a graph, but that's where we stop. When they would like to do maths further at university, they'll differentiate further.
Do you know what kind of careers this is going to go into? Calculus?
Calculus must be. It's the change. It's maths. The change of maths. It's the change of a variable. So any scientific field. If you think of a guy in a rocket ship, if you think of Mark Shuttleworth up in his rocket, we know it's such an excellent example of calculus. I often use it because it's a change of variables the whole time. And the kids ask me, why must we know calculus? And my answer is because one day you're going to go into a rocket ship and you're going to launch from Earth, and it's a change in variables. The faster you go, the higher the rocket goes. The fuel burns up, so the weight of the rocket becomes less. So the higher you go, the lighter the rocket becomes, and that's calculus. It's a change of variables, all at the same time.
Yes, I'm not quite sure how that will apply to the average person.
Not the average person, I suppose, but
no,
a good mathematician,
yes,
and scientist, maybe.
Yes, or someone who's maybe just very rich and able to buy a ticket.
But you know, Helen, also normal, every day when you've got one variable changing something else, it influences in life, anything that influences. If you have to pay more for transport, then your food prices are going to be higher. So it's one thing. It's a variable changes inevitably another variable in life, and that's calculus.
Okay, but surely that's true for all functions. As one variable changes,
Yes.
so does the other.
Yes.
Okay, so what makes calculus unique? I know I'm putting you on the spot here.
I don't know what makes calculus unique, to be quite honest with you, except the fact that you are able to find a gradient at a specific point immediately without even having a set of coordinates. Because you can differentiate, you can find the gradient immediately.
Yeah, the gradient is what's so useful,
Yes.
isn't it? Yes.
On a function anywhere.
Mm.
Quickly.
Yes. And of course, gradient is from grade 9, isn't it?
Yes, and it goes through. And you still have to know gradient in grade 10, again in grade 11, and now in grade 12. For me, it's almost putting everything back into perspective, because you've got an easy gradient formula in grade 11, and then all of a sudden in grade 12, you've got the first principle formula and your short method, which makes it a bit easier.
Okay. And the short method is the rules?
The rules of differentiation. I call it long and short, just so that the kids can always distinguish between which is which, but mathematically correct, it's your first principle, which you use the first principle formula, and your short method is when you use the rules of differentiation.
Yeah.
Yes.
Now, going back to the conversation about where calculus is applicable, what might be an idea is to get them to find ways. And most children have access to, no, not most children, but at some point they have access to Google. I know that some service providers allow you to Google and go onto Wikipedia without having any data costs. so they could possibly find places and come back to you.
Yes, I think better than a rocket scientist, I suppose. Yes,
Yes.
or launching with Mark Shuttleworth. Yes, yes. But they do like my example, I must say. They understand. For me, it's just understanding that at the same time, different things happen. You know, within that space.
Yeah. Okay, now in terms of, obviously it's a grade 12 section, how many marks are we looking at? Which paper is it in?
Calculus is in paper 1.
Okay.
More or less 35 marks. They can go up
Out
to
of 150.
38 out of 150. But it's easy marks. I really believe that calculus is easy marks. Even if you want to do your first principle formula, it's usually 5 marks. It's giveaway marks. Same if you have to differentiate using the rules. If you know your rules, you'll be able to differentiate. If you follow the steps, it's easy marks. The level of difficulty, I think the most difficult they can go is perhaps to substitute a foiling into there, or you must do some distributive law. But other than that, I think it's easy marks, in paper 1 especially.
Do you sell it to the learners as easy marks?
I sell it as easy marks.
Okay, so now I'm sitting in your class. What would you say to me at the beginning of the section?
If we start calculus, I always say, everybody has always got a big thing, because in all previous grades you've heard calculus, calculus, calculus. And it's really listen to the teacher, know your rules, and it's easy marks. And in all the years that I've been teaching, most recently again, we did a standardized test that was just on calculus, and it's the highest mark of all the assessments in term 1, or I've even found at the end of the year, your calculus test is always your highest, because it's rules. It's like exponent laws. If you know them, you know them.
Oh, it's a good pep talk. Shall we get on to what is the content before we go into more in depth into teaching methods, because that's what we want to focus on here. What is the basic content we're covering in this section?
I've said the first thing you would have to explain is the concept of a limit. With the concept of a limit, it's quite difficult. The students find it very difficult, but I've got an investigation that I do with them, or that they can do in groups. This year I actually made them do the investigation in groups. We can have a look at it. I'm not sure if you want to.
I think later we will.
We will.
Yes.
The next thing you teach is your first principle. Most textbooks only calls it the first principle. They don't call it the formula, because the kids might get confused. But this is this guy, where h tends to 0, and we have fx plus h minus fx over h. Once they've got that under the knee or under the belt, we do the rules of differentiation. And the rules of differentiation is this one basic rule that they have to know. And that is, if you've got a coefficient in front of x and you've got an exponent, we differentiate by multiplying the exponent with the coefficient of x. We multiply those two and we subtract 1 from the exponent.
Okay. Okay, now obviously this isn't the whole section. We're just running out of space. So let's talk about these 3 points very quickly over here. What is the reaction when you put this up on the board for the first time?
They get the fright of their lives. If you show them the first principle and you show them that, they get the fright of their lives. What I usually do is I say to them it is exactly the same as using the quadratic formula. The first time in grade 11, when I wrote down the quadratic formula of b squared, that one.
Yeah.
Or I can write it out for you. Minus b squared minus 4ac, quadratic formula. They also got a big fright, but that quickly helped. That minus b plus or minus, as I write it nicely.
No, don't worry.
Anyway, when you've written the formula down, they get the same fright. For me, it's very important that they substitute that and that correctly.
Okay.
Once I've showed that to them, it's much easier. Remember, this says when h tends to naught, the limit, but before that, you've done a limit investigation and they understand the concept of a limit. They do get a fright, but you take it slowly and easily.
Okay, and you did talk earlier about checking that they understood substitution.
Substitution.
And this is, of course, where it comes in.
Yes.
Yes. Okay, well, let's go on to the next things. So we got to rules of differentiation, and of course, you said that was the short method.
That was number 3.
Yeah.
Sorry, I'll go higher up this time. Number 4 was sketching of cubic graphs. And there, again, a lot of previous content comes into play. Grade 11, factorizing, doing the factor and the remainder theorem, very important. Then application of cubic graphs. That is where the graph is given to you and you must find questions or you must find stuff from the graph. The kids struggle with application, but if you've taught them to sketch properly, it'll be much easier. And then they've got word problems in calculus, minima and maxima, word problems. And as soon as you say word problems,
Yeah, they switch off.
they switch off. But, very important, the word problem will always say calculate the minimum area or calculate the maximum volume. And again, it's a clue. If they see the word minima or maxima, what must they do? Differentiate.
And that takes us back to...
And that takes you back to calculus. And they don't have to differentiate with first principle. They can differentiate using the rules of differentiation. But the word sum will have in calculate the maximum volume of the can, or calculate the minimum area for the sheep to graze in. And that's a clue. I tell the kids that I teach, if they see the word minimum or maximum, they have to differentiate.
Now, in a question in a test or an exam, would they be asked that kind of question from the beginning, or would they be scaffolded into the
Always.
minimum and maximum?
Exactly the way that you've been taught. So the calculus section in an exam will have a first principle, and they'll say differentiate using first principle. Then they'll have a few short methods where they'll include some surds, definitely. After the short method, they'll have a minima and a maxima word problem. If not, that sometimes you're lucky and they take that out and they just give you a cubic graph. A lot of the times, the cubic graph will be sketched. The sketch will be given and you will be asked for information from the sketch. It's time consuming to sketch a cubic graph. It must be tested, but usually your teacher will test it in a test before the time. In an exam, it'll be easier if, for example, you have a cubic graph that's already drawn and your teacher will ask coordinates of your stationary points, C and D. Remember, those are your stationary points or your turning points for the graph. In calculus, we call them stationary. The reason we call them stationary is that there's no gradient at those points. Your teacher can ask the distance from A to B.
And that would be your x-intercept?
That'll be your x-intercepts. Your teacher can ask you to calculate the point of inflection, which is very important. And a lot of kids get or struggle with that, a lot of pupils, because that is double derivative. And remember, the notation for double derivative is those little two lines called double derivative is your point of inflection. She can even ask you the length of a C. I've got a C, let's do it E. But they love doing this.
The point of inflection.
Point of inflection, and they love asking you different lengths, because instead of asking you for the coordinates of A, they'll say, what is the length of line AB? Stationary points they love. The reason that they love stationary points is to find your stationary points, you have to have first derivative. In other words, your function given needs to be differentiated using the rules of differentiation.
And they, of course, must remember that they need to do the first derivative at the...
For stationary points, and they must remember to do double derivative for point of inflection.
Now, if they need to find the gradient at any other point...
At any other point, then we can get to your tangent, which I didn't even mention, but you can have your tangent touching your cubic graph. And
Yes.
that you can even be asked to find the equation of the tangent.
And that you would use the derivative again?
You'll use derivative again, because you will, at that point, you'll usually have a point. Let's say it looks more or less like 1 and 3. But at a point, remember that you always do derivative to find the gradient. A tangent will be perpendicular, so the gradient of the tangent will be the inverse of the gradient that you found there. But now I'm getting technical. I'm getting very technical. I can see it on your face.
Now, the point of inflection is something that
Yes.
teachers struggle to explain as well as learners struggle to understand. Have you found any tricks with explaining it that work all the time?
No. I just say, I'll show you. I give you a function of 3x cubed plus 2x plus 6. We find the gradient, we differentiate, and we remember we have to say the exponent times by the coefficient, 3 times 3 is 9, and we have to subtract 1 from the exponent. Again, don't forget that that exponent is a 1. 1 times 2 is 2. X falls away because 1 minus 1 is a 0, and your constant always falls away. That's
now,
first
is
derivative.
this something that they struggle with? The constant falling away?
It's a rule. I give it to him from, we have rules of differentiation. First rule, a constant is always 0. It's a rule, they have to know it. Double differentiation, so all I say to the learners is do it again. 2 times 9 is 18. X, subtract 1 from the exponent, and the constant falls away.
And when they ask why does the constant fall away?
It's a rule. That's what I say. The constant falls away. It's a rule. Or I can say to them,
Yes.
a rule, or better, I'll explain it to you. A constant has an exponent of 1, and we
Yes.
multiply 1 with 6, which would give us the 6 again. And we have to subtract 1 from there. 1 minus 1 is 0, and it falls away.
But anything to the power of 0 is 1.
1. No, Helen, it's a rule. Your constant differentiation falls away.
Okay. The reason it is because it has x to the power of 0 right there.
Which is 1. I
Yes.
could have said that. I
So
didn't think of
0
that.
times 6
Is 0.
is 0, and that's why...
X to the power of 0 will still give you a 0.
Yes.
I almost thought of 1. I almost challenged you on that one.
I was revising
No.
it earlier.
No, I'm looking. Are you right? You are right. I'll remember that. Thank you.
Okay.
But then, okay.
Yes?
But then, ma'am, why won't they write 6x to the power of 0? Why do they write 6?
Then, you see, if it were my class, I would tell them,
But really?
mathematicians are lazy, and we will always find the easiest way to do something, so we always leave off things that we don't want to write down.
That's unnecessary.
Yes. We always find the quickest way, the fastest way. We like step-by-step instructions.
Or if it's my class, I would have just said, it's a rule. You have to know it. But now I know, I'll explain it to them. I haven't had that question before. But I might. I might.
Okay. So the point of inflection, though, double... So we know how to find...
The double derivative.
Yes.
But to find the point of inflection,
Mm.
you have to make that guy equal to 0. Yes. Solve for x.
Okay.
Sub it back into your original fx
Okay.
and find the y coordinate.
Okay.
And then you plot it. Like your stationary point, for your stationary point, you'll take your first derivative, 9x squared plus 2. Remember, this was literally out of my head. Make that equal to 0. Solve for x.
Yes.
X goes back into original to find the corresponding y value. First derivative will 99% of the time be a quadratic because you need 2 x values. If you think of a cubic graph, you've got 2 stationary points most of the time.
Okay, I did see a really nice explanation recently about how to explain the point of inflection, not so much in real terms or anything like that. So
Mhm.
I'm going to show you quickly what I found. And I think the fact that I'm sitting on the opposite side won't make too much of a difference. So we have
A cubic
a
graph.
cubic, something like that. Now if you draw the tangents, let's do a different color, to the cubic function, you'll find that the cubic function has the tangents at the top,
Yes.
over there, and then suddenly the tangents switch over to underneath. And the point at which they switch over to underneath is the point of inflection. Yes? I see you grabbing that pen.
I don't mean to grab. I agree with you. Yes, that's a very good explanation. I also like that. We also say to them the point of inflection is where there is a change in gradient. Or where, but you're saying the same thing. So, for example, we've got an increasing gradient, we've got a stationary gradient, we've got decreasing. Point of inflection, usually after that, it's a change in gradient again. But we're saying the same thing. I didn't think of the tangents though, that they're all on this side and after the point of inflection they change. I will remember that.
I thought it was quite I must admit,
yes.
I only came across it recently. And that's the thing about teaching, is that you always come across new ideas. And
I've learned 2 new things. A very important thing, now that I see your cubic graph, that we also teach, and that even the grade 12 struggle with, is to see that they need to read a graph. And this they need to remember from grade 11, from left to right.
yes.
I have a lot of kids that want to start reading the graph on the wrong side. They have to start like if you were reading from left to right, so that they can see this is an increasing gradient, stationary, nothing happens. It decreases, stationary, and increases again. But I have a lot of kids saying to me that they want to increase that gradient, but they're
Yes.
reading it from the wrong side.
And you find that also in grade 11 with the other
It's
increasing
very important
and
if
decreasing.
you're doing application of graphs that you read your information from the left to the right, like you'll read in a normal situation. Yes.
I've just thought of something else. Usually when you talk about increasing and decreasing, you have a little picture of a car traveling up and
That's
down
right.
and things like that. It would also be good at that point to say, look, it's at the top of the hill, so it's not going to move either direction, so that's why it's the stationary point. It's
For them
it's
to
a small
understand that.
thing.
Yes.
That's the way, if I was still in a classroom, I would do it that way.
Yes, and I often say, for the stationary point, we differentiate, always differentiate, but there at that stationary point, there is no gradient. The gradient is equal to 0. Because they always want to say, why must we make the first derivative equal to 0 to find the stationary points and then show them? Because there nothing happens.
That's a very good point, because the temptation is to just teach to find the stationary points, find the first derivative and make it equal to 0, and not to show them.
To show them why you're making it equal to 0.
Yeah.
Yes. I had a pupil asking me recently, why must the first derivative be equal to 0? And a good thing was to show it on the graph.
Yeah. That's a good thing. Okay. We need to look at the 3 pressure points. You've made a slide for us on the 3 pressure points in differential calculus. Before we do that, if someone is struggling with the content knowledge, and I know the thing with maths teachers is that we teach the same thing, so you almost don't need to revise factorization, whether you're teaching it to grade 9 or grade 11, it's the same thing. But with differential calculus, it's one section that's taught for 3 weeks of the year, and you do need to revise sometimes. So if a grade 12 teacher is needing to do some revision, we do have some videos.
It's very important.
And my first year of teaching high school maths, I must admit I spent a lot of time on the Mindset website, reading, looking at their videos and brushing up on my content knowledge. And this is a perfect way to do it. You do it in the privacy of your own home.
I agree with you, especially to brush up on small things like factorization, the laws of surds.
Yeah. And the best thing is no one can see you.
True.
Yes, so you can learn all of your things while no one else is watching and no one puts you on the spot and says, but why does the constant fall away?
But you know, Helen, you learn.
Yes.
Every day you learn. I've been teaching for 15 years. You've just taught me something new.
So I feel special.
You do.
Okay, there are quite a list of links over there. I will put them on my blog and then we will look at those. Oh, well, you can look at those in your own time.
Thank you.
Now, not you specifically.
I will also look at them.
Yes, but I think they're good TV. Shall we look at your 3 pressure points?
You can, yes.
Okay, your 3 pressure points were
Number one, I think I've mentioned this again, but I'll say it. It's the first principle that they substitute incorrectly. The second pressure point would be your rules of differentiation. Understand why the constant falls away. Rules of differentiation. I'm going to stop there because I always spell it incorrectly.
Okay.
And number 3, for me, is sketching, yes, but more application of your cubic graphs. I have said that before as well. But the application of cubic graphs. And in that point, can I also then include your minima and your maxima word problems?
Yes.
Those are my 3 pressure points, I would say.
Okay, now just to clarify what pressure points are.
Yes.
They're the points at which teachers and students or learners should be especially mindful of what they're doing.
Definitely. Definitely.
So,
especially in first principle, when the function is given and they must substitute it into the first principle formula. I always say to the learners, if they've substituted the second line incorrectly, everything else is wrong. That's very important. Rules of differentiation, know your rules. Remember, with rules of differentiation, to revise your laws of surds. That's taught in grade 11. Teachers can even just give a short worksheet 2 days before you're going to do rules of differentiation. And then application of your cubic graph is where the graph is given.
okay. Well, we've inserted a new section to the show, which is good idea, bad idea, in which we look at 3 points, which should be a good teaching technique versus a bad teaching technique. And the first one is up. The good idea is to teach first principles, or teach first. Is it there meant to be an S at the end?
Teach first principle.
No.
Principle, yeah.
Teach first principle before rules of differentiation, and the bad idea is to teach rules of differentiation before first principle. Tell us why it's a bad idea.
It's such a, everybody's got different ideas. We've done it, I've done it the different way around. I've done rules first before I did first principle, but what I've found is the rules of differentiation is quick and easy. So you've got a long function or a difficult cubic function. Quickly you can see what the answer is. For first principle, for me, it's understanding the concept of derivative, why there is a limit, and then going through the whole process to find the derivative in the end. It's more important. I also find the kids get lazy. They want to they take shortcuts. Instead of showing me all the steps, they know what the answer is because I've showed them the short method. I've had a few of that happening recently where the extra maths teachers have taught them the short method before the first principle. For me, it's better to show them to understand the concept of calculus. First principle, then I show them short. Now, when we're asking them to do first principle, they're more than welcome to do short to check that the answer is correct.
Yes.
That's my first one.
I think you've touched on something really good there, that inherently we're all a little bit lazy, and we'll always go for the easier method, and ultimately mathematicians are lazy people. We always look for the shortest method, so it's a good thing to teach the long one first so that they master it before.
Yes, and to show me all the steps. They must remember to always show all their steps because they get marks for it. even if they went wrong in the substitution, if they went on correctly further, showing me all the steps, they get marks for it. Very important.
Okay, the next one says revise laws of surds before rules of differentiation is a good idea. The bad idea is not linking laws of surds to rules of differentiation. Remind us again quickly what you mean by the laws
of surds. Laws of surds, most of it is done in grade 11. For me, the most important one to remember is that the square root of x is the same as x to the power of a half. And so often pupils forget that. They forget that the square root, remember a square root, has got an imaginary 2 on the outside. Even if we have the cube root of x to the power of 4. Now, how on earth would you differentiate that if you haven't applied the law of surds? In other words, that means always outside. I always teach the pupils that we put outside under, inside on top, but that again, this little 3 will become a fraction. And then if you've got x to the power of a half, to differentiate it's easy. Half times 1 is a half. X to the power of a half minus 1 is minus a half. It's much easier than trying to differentiate the square root.
Okay, I'm just going to quickly draw a little circle around that because it got a little bit lost. So half times the constant in front gives us a half x to the power of negative half.
And the teacher sitting here that always hammers on notation, you can't just go from there to there and say is equal to. You have to say I differentiated. Because in mathematics, x to the power of a half is definitely not equal to a half x to the power of negative 1. That's not true. But you must show the examiner that you've differentiated. And to recap, I take the exponent and I multiply it with the coefficient in front. That's where the half came from. And that exponent is always subtracted with 1. We subtract 1 from it. So, laws of surds, very important, because you get something very difficult to differentiate, but I won't go into that.
Now that's quite a quick revision, isn't it?
It's a quick revision, but they forget that. It's not reteaching. So
maybe 30 seconds to
quickly.
3 minutes in a class. It's a very small change that will make a big difference.
It'll make a big difference, and especially in exams at the end of the year for grade 12, the examiners love asking functions with square roots in them to differentiate. And that's because the pupils forget to change that law.
We keep coming, I know this is your first show with us, but we keep coming back to that problem where they don't want to apply what they do in this section to what they do in that section.
And they can't be isolated at all. They must remember, grade 11 and grade 12, all the work is examined at the end of the year.
And everything can apply to every other section.
Definitely.
Okay, your last good idea, bad idea. Good idea, teaching differentiation before cubic graphs. And your bad idea is teaching cubic graphs before differentiation.
For a cubic graph, to be able to sketch a cubic graph, they have to be able to know how to find the stationary points. They need to know what those sets of coordinates are. If they don't have that set of coordinates, let's say 2 and 5, and this set of coordinates, -7 and 1, they won't be able to sketch it.
Are you sure that's correct?
7 and a -1, other way around. But I'm just going on to my sketch.
Yes.
Can't find the stationary points if they haven't learned how to differentiate a function. They can't find point of inflection. Again, they have to be able to differentiate for stationary points. Point of inflection, they have to be able to find double derivative. Very important to differentiate before you draw a cubic graph. I can also say very important that you've done, they call it factorization of polynomials in the CAPS document.
Yes.
We call it factor and remainder theorem.
Polynomial functions, they call it.
Very important,
Yes.
so that they are able to find x-intercepts and that they are able to factorize a cubic function.
Okay. Shall we go on to your 6-point teaching summary? Most people do 5 points. 6 points needed for calculus?
Yes, I start with, but CAPS does it as well. I always do revise the factor and the remainder theorem. Most textbooks don't do synthetic division, but if any of the teachers have ever heard of synthetic division, that's very quick and very easy. I would suggest that you find out more about synthetic division.
We'll post a link of some resources
I
on
will
the
also
blog.
do that because
Yeah.
it's quicker. I haven't found a textbook with a method in there yet, but I'm more than welcome to show it to you and we can put it on your blog. But it's a quick and easy way of factorizing a cubic equation, and it's called synthetic division. Then I use an investigation to introduce the concept of a limit.
Now, you've spoken about this twice. I hope a little later you'll show us your investigation.
Just so that they understand that if a point gets closer and closer and closer from the left-hand side and the right-hand side, but we can do that again. We then do the gradient from first principle. I then do rules of differentiation. After rules of differentiation, it's sketching of the cubic graph, and then analyzing a graph or interpreting a graph. That's probably a better word. And lastly, it's our word problems, minima and maxima.
Okay, it looks pretty much like the same list you drew up a little
Yes.
earlier. So no surprises there. It's just a nice summary of what's going on. Now let's talk about your investigation, because when we spoke on the phone earlier on, this sounded really exciting. You said that this was the first time you had used this method. So talk us through the process to get to the change in teaching technique.
When I started, when I was much younger, in the early days, it's quite difficult to introduce the concept of calculus. And I had different methods and different ways, and it will just be me talking. And eventually, the kids got so lost, and they had no idea what this teacher is saying. And they have to understand the concept of can I draw it?
Yes.
If you take a parabola, let's just make it an easy parabola, x squared parabola, and we take a point, which is what my investigation basically is, the point 2. And this is a parabola. Remember, that is a good quadratic function of x squared. Not plus 1 or plus 2, because we're turning here. My sketch is not brilliant. But if we take values from the left of 2 and values from the right of 2, and you substitute those values into your function, you will see, and I've got a little table on my investigation that shows them, and I give them values to the left of 2. Those values would be 1, 0, 1, 1.5, 2.5. I give them values to the right of 2. And if you substitute them into the function, getting closer to 2 and closer to 2, that eventually this value will get to more or less 9, or some of them get to 8.99. And to show them that the closer you move to a point, it reaches a limit. And the investigation in groups, they don't believe you. So now you teach this, or you say this to a kid in the class, and they just look at you with wide eyes. My investigation, I actually give them a table with the points.
Yes.
They have to substitute it in and see, do they get closer? What do they get closer to? And amazingly, they don't believe me, but on the 2 different tables, they'll get closer to the value of 9. And I say to them, what have you noticed with those values? What have you noticed with the values to the right? And it just seems to work in one lesson, and it's done.
I must tell you something slightly embarrassing now. That's probably the first time I've understood the concept of a limit.
So
that's a good investigation. Shall we take a look at your worksheet
You
that
can?
you did?
Yeah.
Now, you have very kindly said that we can share this on the blog.
No problem.
And I see that it's got the picture of the parabola. It's slightly better drawn on your worksheet.
Yes, it is.
Yes. And it's got the table at the bottom where it says the left of 3. Oh, you've said x is equals.
I said
X is
less than, I
less
think.
than 3. So
Yes,
it's on the left of 3.
It's on the left. It's just, yeah.
And they would fill in the values there.
They will then work out the values there. They will fill it in. And then I've asked them questions. What can they notice about the value? And now we do the same thing.
Yes.
With the
To the
next
right.
table, we choose values from the right. I choose the values for them just to make it easier and quicker. They substitute into that column, and then eventually they will see that approaching 2 from the left and from the right eventually will bring you to a limit. There's a limit to that function.
Okay. How long would this investigation take? Are we talking a week here?
No, one lesson.
One lesson.
I did it recently. I did it in one lesson.
And I'm sure the amount of time they've spent on this has made it a lot easier to teach the
It
subsequent
was
knowledge.
much easier for me. They explain it in so many different ways, but then the concept of a limit is understood. We do a few limit sums after I've done the investigation, and then I go straight into first principle. And then they understand with my first principle, if I write lim when h tends to 0, it means that inevitably we are getting closer and closer and closer to the value of 0. And they understand it. I go straight into first principle, and what also helps is then this notation of lim h tends to 0 doesn't scare them so much.
Yes. Because it is scary.
It's scary.
It's more scary than the sigma sign.
Yes, you're quite right.
Mm.
So it takes quick and easy, and then we're done.
Okay, and this is an investigation they would do on their own, or do they do better in pairs, in groups?
Last year, I did it individually. I've got a bit stronger of a stronger class this year, and they did it in groups. And it went quickly. One lesson, and we were done.
And did they feed back to you, or did you talk about it afterwards?
I did. I started calculus, and I said to them my whole story about the rocket and about variables that change. And I explained to them that now we've got different variables. You've got different numbers because you approach from the left and you approach from the right. I don't know if I approached to 2. Yes, sorry. And it doesn't matter how many changes of those variables. There was a limit that this graph had. You could only go up to 9. It didn't get higher. The closer you get, and they understood it. Yes, they loved it actually. It was quick and easy, I must admit.
Great. Now you did also bring some other worksheets for us to look at. And I know from our conversations over here that you're a fan of step-by-step procedure.
I am. I think yes.
So why don't you talk us through this worksheet, Rules for Differentiation?
The rules for differentiation, for me, it's a recipe. As long as you know your rules. It's like laws of exponents. If you know your laws of exponents, you can do exponents. Rules of differentiation, I've said it before. I've even put bullets there that they must know. But now I know how to explain that a constant is a 0, that a 2x squared becomes a 4x. And then most important for me, the first part is that they have to know the rules, but the bottom part where it says fractions, because all pupils struggle with fractions. And now
it's like the block. Whenever they see fractions, it's the end of the world.
It's the end of the world. I have mentioned that as well. That's why I put it with my rules, because they have to also learn. If there's a monomial at the bottom, and I've actually typed it out for them,
yes,
they have to split the fraction, and I've given them an example. I think it is A over D. Is it a D? Can't see that far. And a B over D and a C over D, I think. And then I've also said to them, if there's a binomial, that they'll have to be factorizing. And, of course, very important, again, the clue. There's always a clue. If it's a binomial, guaranteed you're going to have to factorize or take out a common factor on top. And if they know that worksheet or those rules, they get full marks. I can add one more thing, and I should actually, and that is your third laws. Remember your third laws when you do rules of differentiation. I should actually include that there, just as a reminder from grade 11.
Now, you put a lot of work into making that worksheet, but you could actually just write it up on the board, couldn't you? And they could write it down in their books. It's not something you have to print out.
No, you don't have to print it out. They can just write it down. Definitely.
Yeah.
Definitely. It's just me. I always want them to have it in their books, but they can write it down. Yes.
Yeah. And of course, if you print it out, then it's more likely that they'll stick it in.
That they will. I have noticed recently we wrote another test in my class, and they had to go back to calculus. And one of the girls said, I have never told them there's a monomial if there's a mo. And we went back, and we could show her the note. So it's very good. It's very good to have, and it's good for the kids to have a recipe.
Yes.
Step-by-step recipe.
Don't you love that? You've never taught me this.
You've never?
Yes. It's not my fault that I didn't learn.
You'll see it's the same for cubic graphs. The sketching of cubic graphs, I've also made a sheet where I have steps that they have to follow.
And have you brought that with you today?
Yes, I think we've got it here.
Well, let's take a look quickly at that.
It was...
Oh, yes, I see. Once again, step 1, step 2, step 3.
Those are different notations.
Okay, different notations.
There's your cubic graphs. Step 1, step 2, step 3, step 4. And it's all about what to do first. The first thing is, for most of them, I even write step 1, draw a
Cartesian plane.
Cartesian plane. I think that's my last step. But yes, for me to follow steps is important.
And that way they don't leave anything out. I think from a teaching point of view, it's also a good idea to have a mental checklist in your head. I have covered that they must label their axes or whatever small step it is.
I have said in that cubic graph one, we start with very basic. We start with finding the x-intercepts, finding the y-intercepts, and then the stationary points where they have to differentiate. And I show them, find f of x, and in step 4, or step 5, I think it's a double derivative. So for them, it's just a recipe on how to sketch a cubic graph.
Now, do you find that they understand it, or are they just following a recipe?
No, I do think they understand it. For them, it was very daunting when I said, and now we're going to draw a cubic graph. Because up to grade 11, they have been doing a lot of functions, but they were hyperbolas and parabolas and straight lines. I don't want to say basic, but they've never ever thought that they can curve another time, that there can be 3 x-intercepts, or that there are 2 turning points. And the first thing I said to them at the end of calculus, you're going to draw a cubic graph, and they all said never. And if you say functions or word problems, any learner always goes, they hate functions and they hate word problems.
Yeah.
But I think by giving them a step-by-step guide, it just puts them at ease, especially with functions, because it's almost like fractions.
And it's almost by doing more of them, they understand more of what they're doing.
Definitely. And I've also found that they often correct me, that I'll do x-intercept and then y-intercept, and they'll say, but your steps were on the note that you do y-intercept first and then x-intercept.
It's actually a nice intentional error, actually.
Yes.
To stand there and do something out of order and see if they pick it up. And
they definitely do, because they're so used to me doing it that way. I think a lot of kids can find it difficult as well, because there's always structure, but I suppose in a subject like mathematics, for me, there has to be a bit of structure. You can't just be all over the place.
Yeah.
That's especially in a concept like with calculus as well.
Yeah. I used to have a maths lecturer. We all had maths lecturers. But she used to say, when she was teaching, that she would tell her students that I'm going to make one error today, and whoever finds it first will get extra credit or whatever it is. And so it kept them on their toes to constantly watch out for this error. Of course, the error would never be intentional, but it would keep them thinking critically about what she was doing.
That's awesome. I must remember that, because I've got 2 very intelligent grade 11s in my class at the moment, always looking for mistakes. But maybe I must make an and say the first one to find it. That'll be a very
It
good
does also
idea.
lift the pressure off the teacher.
It does.
'Cause,
It does.
Well done, you spotted it. I hit it there, craft. Okay, and mistakes often happen, especially with the rules of differentiation. It's so easy to make a careless slip there, especially as a teacher where you think, I know this, I do this every day, it's okay. And you do make a slip. You forget to minus the 1 from the exponent or
I often
whatever
find
it
I
is.
work fast. You know, time is always an issue, and we need to get through the work and we need to finish. And if it's a time thing, I do make errors. But the kids will quickly say, the pupils will quickly tell me, ma'am, you've done that wrong, or you said 2 times 2 is 6, or
Yes.
and I just say, oh, sorry, and I continue. It's human. Teachers must remember that.
Well, thank you for all that. We have time for one last thing, so let's get into that. Okay, now one last thing is once again taken from the book Teach Like a Champion by Doug Lemov. And this time the actionable step is stretch it. Now, 2 weeks ago we had the step no opt-out, which said every child who's asked a question in class must give an answer, and it must preferably be the right answer. And we had various strategies that we could do to get the right answer out of children, and one of them was to say what is 2 times 3, and Twanette can't answer it, so we go to Dylan and we say what is 2 times 3, and he says that's 6, so we go back to Twanette and ask the exact same question so that Twanette does get the right answer. And the thought behind that was that students will always listen to everything so that they're not caught off guard and they have to give the answer at any point. Then the next week or last week, right is right was the strategy where every answer had to be completely right. And this is the one that I didn't quite agree with. I thought that you should acknowledge a half right answer, but acknowledge the fact that it's half right, and then look for the full right answer elsewhere so that everyone knows Twanette got it half right, but Dylan completed the whole thing and got it 100% right.
I agree with you.
Then today, stretch it is once you've got the correct answer, you reward that with more knowledge. So you don't say, there, boy. We say, well, now that you know that 2 times 3 is 6, what is 2 times 3 times 2? So we take the knowledge a step further, take the questioning technique a bit further, apply the skill in a slightly different context, or maybe even apply the skill in a completely different context. And just carry on extending that. I quite like this one because it extends those who...
It does extend. It depends on your crowd. It depends on the pupils in your class, I would say.
Yeah.
But mostly, when we're in grade 11 and grade 12, mathematics content-wise, if the pupil is able to answer you or give you the correct answer, personally, I would just say, well done. Awesome.
Yes.
Thank you for that. Let's move on. You get your clever ones that I'll stretch a little bit further. But the content is difficult, so I suppose it depends on what you're busy with at that moment.
Yeah, it does depend.
And also a teenager, just to get them to answer.
Yeah.
You're lucky if they actually answer. And if I have to by name ask them to answer. But it's just the way the teenagers' makeup is. And then if they do answer, and I want to say incorrectly or correctly, I will always encourage them, and I'll always say, well done, you're almost right. You almost knew what a polynomial is, but it's not 3 terms, it's 3 or more terms. So just good, well done, but that's just my advice.
No, I quite, as I said earlier, I think recognition should be given where someone has got partial correct, but also acknowledge that it's not all the way correct. This man, Doug, says that you should get someone else to say it's 3 or more terms, not the teacher. So
yes. But I just said about that 1 or 2 clever boys in my grade 11 class currently. they're very quick to correct me also, which I appreciate. It's a good thing. But then I think once they've corrected me, I can also then challenge them with, but now what if I add another 3?
And that's exactly
or what if we divide by 8?
Yes.
Very good. Very
Yes.
good. I'll remember that.
It's quite a rare skill as a maths teacher to be okay with people correcting you. Well done.
Oh, thank you. Well, yes, I suppose so. But, you know, there are times that you make a mistake and then they correct you. But I think I correct them more often. So
Yes.
it equals out, you know?
Yes.
Yeah. I always say that. And they'll always say, ma'am, and then I'll say, yes, but yesterday, and then we finish the conversation.
Yes, that's a good way to deal.
Mm-hmm.
Okay, well, thank you very much for joining us, Twanette.
It was so nice having me. Thank you.
Yes, it was good having you. And thank you, Dylan, for controlling the buttons. And join us again not next week. Next week, government schools are off for the week, so we're actually taking a break. The week after, we'll be going back to grade 10 and we'll be doing trigonometric functions.
That's a difficult one.
Yes, for grade 10s, they don't like it.
They don't like it. But luckily, we don't move them yet. We move them up and down, but not left and right.
Yes.
Thank goodness. So be grateful.
Thank you for joining us. We'll see you soon. Goodbye.
Bye.